As continuing the Earth resistance evaluation and the Earth potential, by the last session we find out that if we are going far away from the electrode 10 times, the Rg, which is the ground resistance, reduced 90%. So in the case of the calculation of the earth potential, it is very clear that the earth potential is the Rg, which is the ground resistance or the earth resistance times current, which is passing through that area. So for two different view, one is from zero, means from inside the conductor, until R, means I think is related to the R0, the maximum point on the surface of the conductor, which is rho, resistivity of the ground, over 2 pi hemisphere, semi-hemisphere I over R0. But in the case of V R, when the R extended to infinity, between the R0 until, or R any area until infinity, you can see the value is I over R. So we can continuing understand of this topic by an example. Mentioned that the hemispherical electrode is buried in the soil with the resistivity of 100 ohms time meter. If the radius of electrode is 1 meter, what is the earth resistance? If the earth resistance doesn't allow exceed 5 meter, again recalculate. So it's very clear, Rg is rho over 2 pi R0, so 100 is rho, R0 mentioned by here 1 meter for the first. So the total resistance is for Rg is 15.92. In the case of the second part of question, you can see Rg should be limited to 5. So we know Rg, then rho also is given. Now we have to calculate the R0 by here. So from rearranging this equation, R0 should be more than 3.18 meter, which is not physically acceptable, but in the case of the example we can consider it. So last part, it asks you to find the voltage, earth potential between two different area, which one is given by the 3.18, which is for the last, the area is for the last, and the new one is 30 meter, and the voltage difference using the equation given by here, this equation 5, we can calculate the voltage around 900 volts. But you have to know, and you have to consider the case, by increasing the distance from the electrode, the voltage drop, because as we mentioned before, if we going away from the electrode surface connecting to the ground, our ground resistance reduce significantly. So if you can remember, by the 10 times, around 90% reduce. So it's function of the distance x, and you can see here rectangular hyperbola shape, which is given by here 3.10, and the 3.9, this one 3.10 is a 3D one, 3.10b, 3.10a is a 2D, which you can see if we zoom in, you can see we have the maximum voltage at the point of R0, and if we increase the distance, means going away from electrode, this is the surface, R0 is the surface of electrode, and if we go further away from electrode, the voltage drop. So here you can see if we check the voltage as 5R0, the voltage should be Vg, which is the voltage as I mentioned at the surface of the electrode R0 over 5. So if we go further 5 times, it reduces 5 times. You should note that we should note that this voltage drop due to usually we have more than one earth electrode. So if the earth electrode need to be connected to the ground in different area, we should consider a case which is virtually zero earth potential. Means none of the electrode should have potentially affect the other, which for this one, as you can see in the previous case, we consider infinity, but here the infinity for us is meaningless. But in the case of the practical application, you have to consider the distance of an electrode to be 5 times length of their radius. If the electrode has no circular shape, so whatever you can find the R for them, then 5 times R should be considered in the case of that electrode. Okay. As I mentioned this one in the previous slide, here we have independent and interacting earth electrodes. Now assume we have two electrodes which are connected to the ground, the same shape as you can see in parallel, identical with each other, identical hemispherical conductors A and B. The radius for both of them are R0, this one A R0, B R0, and the distance between these two electrodes is considered as D. This is we connect two electrodes in parallel due to reducing the earth resistance, and if we reduce the earth resistance, because the potential means earth potential is in direct relation with the earth resistance means times I, the earth potential also reduce. So here you can see the configuration that I mentioned, two electrode R0, A, B, and the current come in here is the current here can be seen as I, so I over 2 for electrode A and I over 2 for electrode B is expected. Then if the electrodes are too close to each other, as I mentioned, should be at least 5 times of the radius, you can see the shape, the graph for this one should be like this. Means if we increasing the distance, the voltage have to reduce, but in this case when they are close to each other, you can see the voltage linked to the other one, which have to follow. Let me draw a bit saving before. So the voltage should reduce in this way by increasing the distance. However, it is connecting to the electrode B, so this area is an equipotential area for these two, which means these two are connected to each other. Then this causing the change in the shape of the total potential. For calculating the potential for two electrodes, we use superposition principle, considering the contribution of each electrode separately. So you can see by here the total ground voltage is subjected of the total ground resistance times current. Here we assume A as reference and the B is considered as a part of A. So here you can see VA in the radius of R plus VB, which is in distance D minus R0. Of course you can understand what's the meaning of the D minus R0. The distance between center of each one, A and B, is D, and R0 is the radius for each one. Here you can see I over 2 is the current, as I mentioned here. I over 2, this is I over 2, I over 2. And we know rho over 2 pi R0 is the formula to calculate the ground resistance. This is for A, this for B is D minus R0. So the final equation reached to the value rho over 4 pi R0, 1 over 1 minus R0 divided by D times I. This is the voltage. So this is the final number 10 is the final formula to calculate the RG total. If there is no interconnection between these two and there is no affecting between electrode A and B, only the highlighted one, the red one, is considered as a RG total. However, when these two have equipotential connection with each other, the other term, which is this one, also have to be considered. Okay, continuing with example 2, hemispherical electrode A with the radius of 1 meter is buried in a soil with resistivity of 100. So the rho is given, the R0 also is given. If the same electrode B is buried in the same soil as electrode A, the distance of the two electrode center is 10 meter. So this is the D. Calculate the earth resistance of the two electrodes. So easy peasy. We can use the equation number 10. Rho is given 100, R0 is 1, and D is 10. So easily you can find the value for resistance, total resistance. In part B, it mentioned if the distance between A and B increased to 100 meter, so we're expecting that the RG total reduced significantly, because 10 meter compared with 100 meter, 10 times increasing. But here, if you're replacing the D, previous one was 10, here it become 100, you can see 8.8, just reduce it to 8.0. So for me, it means after few meters, which is 5 times of R0, or up to you if you want to see practically more than 10 meter, the RG total saturated. And if even you increase it on behalf of 100, you increase it to 1000 meter, which means 1 kilometer, it not reducing more than 7 point, it reached to 7.9 something. So the second term, as we mentioned here, 1 over 1 minus RO divided by D is considered in the case that we are going for the true parallel connection. between two conductor. So in this case, I think the meaning of a true parallel is very important in the case of parallel to electrode in the real case. So when we can have a true parallel electrode is a good question for the exam. As a coefficient or multiplier increase, the Earth's resistance can be thought as an additional resistance Ra. In the case of having two electrodes connected to the ground, we have another resistance. We can have another resistance, as you can see in this figure. We have two electrodes, electrode A and electrode B. Ra is a ground resistance, is a real ground resistance for that area. Of course, for me and for electrical engineering VU, the resistance of the ground can be changed due to the location and due to the last time I mentioned due to the moisture or vaporized river side or any the mineral, anything related to the case. In some cases, real estate constraint may impose a very close placement of an earth electrode. This arrangement limits the grounding system interface capability with the earth and reduce the effectiveness of the performance of adding more electrode. It means that for me, it means that in some cases we cannot add any more electrode to the ground due to interfaces or mutual effect on each other. So in that case, you have to consider another way to reducing the RG if you need. Two or more ground electrode can be considered independently when their electric potential are not significantly affected by their reciprocal influence due to their own geometrical and relative positions. So this is very important in some cases. I can remember an example in the substation that the ground resistance have to significantly reduce for lightning problems and challenges. So we have to install more grounding rod in this case. So we have to consider this, the meaning of the mutual potential on each rod. In the case that we going to consider effect of mutual or reciprocal effect of the electrode on each other, of course we have two different voltages for electrode number 1, which is the own one is R11, or this is the Thevenin one, and R12 effect of 2 on 1 is considered as this one, and I1 here is assigned to said, okay, maybe we have two different value of voltages, means the current means the current is not divided in the same. We have different electrode, different grounding, everything is different. And VG total number 2 is the effect of the number 1 on number 2 resistance, and the own one means the Thevenin one, and the I total of course is current 1 and current 2. So in the case that we need to covering the here the RG total means the total current, we have to consider V total and I total. I total is given, but V total have to calculate it by these values which I mentioned. But in the real case, but more or less in the real case, the effect of a mutual resistance are negligible, and you can cancel the value for that too. So for me, if you cancel these two, it means that R1 means electrode 1 is in parallel with R2. You can see by here R1 parallel with R2 is a total R. In the real practical installation, the electrodes have be optimizing in the placing, means grounding place, because they requires to have a little interaction with each other to controlling the ground resistance. So the interaction between them have to be considered. Here again it mentioned for the practical action, the R, the D, the distance between two electrode and more, should be more than 5 times of the radius. In the case of installing more and more electrode in a ground for one place or for one substation, finally we reach to this graph, which means the number of the rods in the group, how many rods you install from 1 to 16, and the effectiveness in reducing the resistance is considered by here. So after few installation, as you can see by here, the resistance of the ground is saturated, as it's mentioned by here, is saturated, and no need to install anymore. Or if you want to increase the cost on the substation, you can install more. Now we know how to calculate the RG, or the resistance of the ground, and we are going to find out the voltage exposure of ECP upon ground fault. If we have a ground fault, what is the effect on ECP, which is the case of washing machine or any metallic case or any other metallic equipment around you. So if any single line to ground fault happen, and then the person's touching that enclosure closed loop between the faulty metal frame and the earth, due to its conductive nature, will carry the fault current toward the source. So if you touch, or anybody touch, you will carry the current toward the source. As you can see by here, RG here is the ground resistance, and VG is the voltage of the ground resistance, or ground potential, and the I is the current given by the fault. So VG, as it's very clear here, if you want you can use the KVL from here to the ground, the KVL, which you have learned in the semester 3 at least. The VG is equal to RG times I. So the voltage across the ECPs can be easily calculated. Then this voltage is between any point on the electrode surface and infinity. Its magnitude is generally less than the phase voltage. So consider this case. Of course, the voltage here is not the same as the phase voltage, but somehow is the function or proportion to that one. In the case that ECP is not grounded properly, any touching of the ECP, you will affected by the phase voltage, phase to ground potential. So this is practically dangerous situation, as in the absence of a clear path to the ground, the fault cannot be cleared. Now we are going to consider a human, or any, of course, human. A human in the case of the touching ECP. So before that, we have to consider the human body condition, the situation and condition of the human, how it is considered in the case of the fault. So as I mentioned before, we have a resistance body which depend to something you eaten, and this body resistance is given by RB, and we have another resistance which is resistance of the person to the ground, which is in the case of your shoe, or even if you are in the bare foot, between your foot and the ground, whatever. This one is given by RGB. So the RGB is due to the presence of the floor, whose the resistance in the dry condition is at least 1k ohm. So we expecting RGB be around 1k. So from here, the human is considered as because having 2 feet, of course, is considered as a 2 electrode, each feet 1 electrode. And you learn from previous slides that 2 rho, why 2 rho? Because we have 2 foot, over 5 r, which r here is considered 5r, means the electrode should have at least 5 times of the distance with the radius of 5 times. The r is considered for your foot, or my foot, means the foot is 0.1 meter, so this times this one become 4p. So our foot is here considered as a 4 rho, where rho is the superficial soil resistivity in ohm meter. Then the human body resistance to ground, RBG, is equal to 2 rho.